think about how satellites keep out of each other's way while in orbit around the planet. So the first satellite comes up in the 60s, or maybe it was the 50s. And I think it was a Russian satellite, wasn't it? They got the first one up. And it doesn't have to worry about anything. There isn't anybody else up in orbit. Then eventually the Americans get one up. It doesn't take them much longer. And if it's trying to keep its distance from the Russian satellite, make sure they don't bump into each other, it'll take up an orbit probably on exactly the opposite side of the planet. That's the easiest thing to do. And it gives us a very regular pattern to the position of those satellites as they move around the Earth. It gives us a pattern which is linear. Okay? Seems nice and easy. Then after some time passes, then, let's see, who is next? I think it was the British. I could be wrong. So finally the British get one up. And of course, being the British, they perfect it and make it the best satellite possible.
Yeah.
Goes without saying. Silence! And now, with 3 satellites around the planet, again, no matter where they move around the planet, because their #1 goal is to not clash into each other, it sets up a very regular set of positions and alignment for those satellites. Alignment which looks pretty much like a triangle. Okay? So as they move around, it's very easy to predict the shape we get when we connect up the dots. Likewise, and after some time, the Chinese, I guess, eventually get a satellite up, probably copied from the British, because that's what they always do. But, you know, well, what can we do? If you're interested in espionage stuff like that when I was a boy, you find out some very interesting stories about real things that went on. Anyway, 4 satellites around. Again, it gives a very regular shape and positioning to those satellites. Now, I put it to you that those satellites are reacting rather like electrons around a central atom. They've got to stay in orbit, or they've got to stay in the outer shell of the atom, and they've also got to stay as far apart from each other as possible, like negatively charged pairs of electrons, staying as far apart from each other as possible. So if we can make predictions about how the electrons are going to respond to all the other electrons which are around them, we can predict the position of the electrons. And because the electrons, pairs of electrons, connect atoms through chemical bonds, we can also make predictions about the position of the atoms, which therefore allows us to make predictions about shape of the molecule. By predicting where these electrons are. So if we go back to our CO2 example, our carbon dioxide example, we said it was a carbon in the centre, double bonded to oxygens on each side. So from the carbon perspective, it sees 2 chemical bonds. So remember those 4 electrons in the double bond, they've got to occupy space which is mutual to the 2 atoms. So it's got to be in direct overlap of orbitals. So although there's 2 chemical bonds, for the moment we're going to think about them as just being one unit, one set of electrons, because they're limited in where they can move. It does generate more energy for the bond when there's twice as many, because those electrons repel each other. But just think of the double bonds or triple bonds as one set of electrons. So one double bond on one side and another double bond on the other. They get as far away from each other as possible, and it makes a molecule which is linear. A bond angle of 180 degrees. Every time when there are 2 chemical bonds distancing themselves from each other. So those pages in your notes with the VSEPR shapes, it's all about understanding how many bonding pairs and lone pairs of electrons we have. The good thing about it is we're only going to look at shapes from those 2 pages. There's nothing else we're going to address. So all of those combinations are unique on those 2 pages. very particular number of bonding pairs, a very particular number of lone pairs. And I digress for a second. There's another video where you see the green screen effect and the actual page of notes comes up. But look, for example, when we have a central atom, and we're not necessarily talking about carbon, but a central atom with 3 sets of electrons. So we're looking at the second example on that page. And the first example is with 3 chemical bonds. And those chemical bonds get as far away from each other as possible. So they set themselves up in the same plane, but in the points of a triangle for those bonds. Which is why we describe this shape as trigonal planar. If one of those bonds becomes a lone pair of electrons, the electrons, that lone pair, still take up position in the same position where the chemical bonds used to be, because they're being repelled by the 2 bonding pairs of electrons. So the electron position is still trigonoplanar, but the shape we see, because of the atoms attached, boom, 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 the shape is actually non-linear. And then if another one of those bonds is just a lone pair of electrons, the position of the electrons is still the same, because they're still being repelled by each other and trying to keep as far away from each other as possible. And now, with just 2 atoms, we just see a linear shape. Let's think quickly about the examples on that second page, when we have 4 sets of electrons around the central atom. And that was when we had a tetrahedral molecule with 4 sets. So it's almost like a tripod stand. Let me just build that. You can use that in the models there to do this as well. Take one of the black beads. So our methane molecule, CH4, looks a bit like a camera stand, a tripod stand, with a flagpole coming out of the top. But it's a highly symmetrical molecule. Whichever way we stand it up, we get the exact same shape, because these bond angles have been maximized to keep the electrons as far apart from each other as possible, while still being in orbit around that central atom. You've got to fill up that shell. So by maximizing the bond angle, we minimize repulsion and we minimize the energy of the molecule. Maximize bond angle and therefore minimize repulsion from negatively charged pairs of electrons and minimize the energy. And molecules are always looking for the easiest way out, the energy of least resistance, the lowest energy. So we call this shape from the atom positions, we call it a tetrahedral molecule. Because if you join up the white hydrogens, it actually makes up the points and sides of a tetrahedron, a pyramid, 3-sided pyramid. Okay? It keeps the electrons as far away as possible. Now, if one of those bonds on another molecule is actually just a lone pair, that lone pair is sitting on the top of the molecule, but it generates stronger forces of repulsion than the bonding pair. This lone pair isn't being shared with anyone else, so the atom holds those electrons more tightly. It's not fighting with another atom for those electrons. So if it holds those electrons more closely, it generates stronger repulsions to the bonding pairs. How do they alleviate that? Well, they push closer together. So the bond angle now goes down. Before, when it was tetrahedral, the bond angle was about 109.4. Now as a truncated tetrahedral, or trigonal, oh I like this blue pen, trigonal pyramidal, the trigonal pyramidal, the bond angle is now about 107 degrees each time. Lone pairs generate stronger repulsions than bonding pairs. So the bonding pairs have to shuffle slightly closer together and tighten up. But the general position of the electrons, remember there's a lone pair sitting on the top here. The position of the electrons is still fundamentally tetrahedral. But there isn't physically an atom here now. So the atoms we see make it a truncated tetrahedral or trigonal pyramid. In Britain we say truncated tetrahedral, in America we say trigonal pyramid. I think the British term makes more sense after having just seen the tetrahedral. Then it always makes more sense in Britain. Anyways, let's move on before I get lynched. If another lone pair is taken out, another chemical bond is taken out, and this becomes just another lone pair, those two lone pairs together generate stronger repulsions than a bonding pair. So the bond angle between the atoms actually gets smaller again. The bond angle goes down to about 104. And the shape of the molecule from the atoms attached is just boom, 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 non-linear. Or bent, sometimes say. The electron positions is still the same, but there's not physically atoms to give shape now at those points. Okay. So anyway, again, there's already some video up which explains all of those shapes. I just wanted to address that again for a second. So